some okay. Again, this talk will be based on this work we put out with Jaishin in July, and some of the stuff is also based on this earlier paper we wrote with Slava and Jaishin. So this project started out with a project about two-dimensional conformal field theory, and then later we realized that some of the theorems that we prove in our work has some implication in terms of near extremal black holes, especially in context of holographic CFTs, which basically means we are looking at some family of CFTs with central charge going to infinity limit. So the premise of today's talk will be 2D unitary CFT, where central charge is bigger than 1, strictly bigger than 1. And I will also assume modular invariance of the partition function. And I will assume twist gap in the Virasoro primary, which basically means that we have the vacuum state, which is vacuum 0, h is 0, h bar is 0. And then all other states has h, h bar with none of them being equal to 0. So there is no higher spins. And in this setup, we will try to understand the universality in the asymptotic data of this kind of CFTs. And on the ADS CFT, using the ADS CFT dictionary, this basically means we will be talking about BTC black holes in ADS3, and we will learn about the asymptotic growth of states, the entropy, and this kind of things on this side. And just to be clear, when I say twist, this basically means twice times minimum of h, h bar. So there is the twist gap, basically means there is no state in the spectrum with h and h bar being 0 except for the vacuum. So moving on, when I say asymptotic data, I specifically focus on Cardy-like formulas. So we'll be in this talk, we'll be probing Cardy-like formulas for density of Virasoro primaries with large spin and small twist. And again, by using the ADS dictionary, this basically means we will be looking at some rotating BTC black hole in the near extremal limit. So this near extremal limit corresponds to this statement on the CFT side, which basically means we are looking at large spin and small twist. And in the various part of the talks, I will be mentioning about Schwarzian sector. So which in the context of CFT basically means if we compute the partition function of the near extremal BTC black hole, then there should be some factor which looks like this. And the presence of this factor can also be explained using gravitational path integral, which people generally call a Schwarzian sector. Today, the idea is to look at the 2D conformal field theory and try to see whether we can identify this presence of this universal Schwarzian sector in the spectrum of large spin, small twist Virasoro primaries. So now the next immediate question is, what do you mean by small twist? What is the quantification of this number? So there is a natural quantity that appears with 2D CFT, which is central charge. So when I say small twist, I basically mean something which is related to central charge. In particular, I mean the twist around this spatial number c minus 1 over 12. And for the kind of CFTs we are looking at, which is 2D, which is modular invariance, unitary, c greater than 1, and twist gap in the spectrum of Virasoro primaries, this number is very special because we can show that even if we assume a twist gap, the twist gap cannot be arbitrarily large. Just by modular invariance, you can show that the twist gap has to be less than equals to c minus 1 over 12. So this number is very special. And not only that, this point is also an accumulation point, which basically means in the twist spectrum, if you consider an open interval around this point, there has to be infinitely many states in that open interval. So this was first argued by Tom Hartman, which appeared in a paper by Shi-In and collaborators. And very recently with Jaishin and Slava, we basically proved this as a consequence of our theorem. And later I'll go through the proof, at least sketch out the proof. So our aim would be to derive some Cardy formula for density of Virasoro primaries with large spin and twist around c minus 1 over 12. Now this kind of formula is not entirely new, because again people have understood before that there should be an accumulation point, And some naive analysis would immediately give you some Cardi-like formula for this for density of states of Virasoro primaries in this regime. But the main point I want to focus on is that fact that the density of states is really a distribution. So if you consider a compact CFT, all the states are discrete. So whenever we say something like something about Cardi-like formula, we basically means some mirrored density of states. So the idea is to look at density of Virasoro primaries over some small interval and integrate the density over some small interval. And this smoothen out portion of the density will have some Cardi-like growth. So the next question is, the point is we would be looking at this integrated or average density of states to make sense of the distribution. And the next question we're going to ask is the following, that whether there is any universality in the size of the averaging window. So it basically will tell us about the spacing of the microstates in this particular regime. So we are trying to probe, so the point is that we are trying to probe some finer information about the distribution of Virasoro primaries with large spin and twist around this point. And the key in pictorially we can say it like you can imagine this thing. So there is H and H bar plane, which is basically two quantum numbers, and these blue lines are the fixed spin lines, and this A is the point which is basically the twist accumulation point. In terms of H and H bar, it is C minus 1 over 24. So we are basically looking at this region around this C minus 1 over 24 with the fixed spin. And then we are going to large spin limits. So basically, we are counting the number of states in this window and taking the spin going to infinity limit. And we are trying to see how many states are there as we go up and up. And we can possibly try to make this window smaller and smaller as we go up. So that's the concrete question. And we also want to make some quantitative statement about the size of the window, which guarantees that there at least exists such large number of states in this window. And the key tools that we are going to use to probe this kind of statement are something is very well known in analytic number theory, which is called Taubert-like theorems. In number theory, oftentimes you count primes and other things in some small interval. And one way to rigorously estimate the number of quantities in some lying in some interval or make some statement about the size of these intervals is to use this kind of theorems. So we are not going to directly use these theorems, but the main lesson is that we are going to learn something from some techniques that the mathematicians use for proving these theorems, and we will implement these techniques in our familiar setup of the 2D CFT. Okay. Moving on, so as I was saying, we want to look at the number of states in this window as spin goes to infinity. And one way to encode this information is to look at the partition function in some particular limit. So we want to look at the 2D CFT partition function, where we turn on both the left over temperature and the right over temperature. So beta L and beta R are the inverse temperature. And we want to study this quantity in something known as double Lightcone limit. So what is this limit? This limit is basically, so you can think like this: in the usual Cardi formula, the way we derive the usual Cardi formula, we take the high temperature limit, which is basically beta going to 0 limit. So the idea is whenever we are taking some inverse temperature to 0 limit, we are basically probing some asymptote. So here in the H bar plane, basically in the H bar direction, we are going in the high H bar limit. On the other hand, with H, we are near the origin. So basically that boils down to looking at some limit which is like this, where beta L, which is the conjugate variable of H, goes to infinity, and beta R, which is the conjugate variable of H bar, this goes to 0. So this basically makes sure that we are probing some regime like this. And this limit has to be taken simultaneously, and the way we take this limit is determined by this extra factor, which we call curly VW, which is given by this particular quantity, where this capital T is the twist gap that we impose on the theory. And here, one crucial point is that assuming a twist gap is important, because if we assume the twist gap is 0, that there are higher states, then we can never satisfy this condition, because then T equals 0 and then this goes to minus infinity. So it's very important for us to have a twist gap in the spectrum. And later we'll see that having the twist gap in the spectrum basically ensures that the vacuum dominates in the dual channel. Okay. And we also need this condition to make sure that these windows become smaller and smaller, as we will see later. Okay. So moving on, like zooming out, like the thing we are going to do is we want to look at this partition function in this limit beta L to infinity, beta R to 0. These are simultaneous limits, so we have to make sure that beta R inverse is the largest parameter in the game, so it is much bigger than beta L, and beta L is much bigger than logarithm of beta R. And using this thing and using Tauberian-like tools, we are going to say something about the size of the averaging window. And these two information says something about the near extremal black holes when we translate these results in the regime where central charge is very large. Is there any question at this point? Moving on. So here's the plan for the rest of the talk.
So I
Yeah.
will draw the relation between size. Do you mean minus log beta R?
Oh, yes, because beta R goes to 0.
Yeah.
Yes, absolutely. Right. Yeah, I should have been careful. Basically, this thing means this relation. Beta L inverse log beta R goes to 0. So the plan of the rest of the talk is following. So we are first going to show the twist accumulation result in fixed central charge. So basically, this amounts to analyzing the partition function in the grand canonical ensemble, where we have both the left mover and the right movers. And then we are going to do the same thing for the large central charge regime, and this is where the connection to the near extremal black holes comes. And then we will go from the grand canonical ensemble to the microcanonical ensemble, where we make some statement about the number of states, leaving number of states with large spin and small twist. And we will count the operators. We will make some statement about the universality of size of window. And then I will give a quick sketch of the proof. And if time permits, I might mention about some extension when we have extra currents in the game.
Can I ask something?
Yeah.
You said you put the upper bound on tau gap to be C minus 1 over 12.
Yeah.
Wasn't there an improved version, C minus 1 over 16?
Okay, that's an important point. So, well, first of all, there is no so the way that paper works is following. So they assume the Cardy formula works for a very small narrow interval around this C minus 1 over 12. So I was saying I was talking about a small interval around C minus 1 over 12. They assume the Cardy formula works for a small interval which is of the order exponentials minus square root j. To begin with, there is no guarantee that you can trust Cardy formula for a very small regime, because it's a distribution and there is no as such proof that it should work for exponential minus square root j window. And given the statement, even if you assume that that statement is true, suppose you are only working with CFTs where you put it as an assumption, then they show that there is a negativity in the density of states. And then to cure that density negativity, they say that if you put some extra states below C minus 1 over 16, then that cures the negativity. But the implication is in the other direction. It's not really a proof, even if you assume that. In fact, Henry Maxwell and Turiachi has some other proposal to cure this negativity by shifting the BTZ threshold. But this C minus 1 over 12 is a theorem under the conditions I just mentioned, that modular invariance, unitarity, C greater than 1, and twist gap. Thanks. So moving on. So as I was saying, first I will explain the twist accumulation result by looking at this limit. Again, this should be minus log beta r. So our main handle in the game is modular invariance. So we will be using the modular crossing equation, and we want to show that there are lots of states around this in this regime, a minus epsilon, a plus epsilon, where by a I mean c minus 1 over 12. So first we write down the partition function in the direct channel. So there are states contributing from 0 to a minus epsilon. There are high twist states, and then there the regime which we want to show gives the dominant contribution. Then we write down a dual channel expansion, which is basically doing an S transform and evaluating the partition function at 4 pi square over beta L and 4 pi square over beta R. And then there are two contributions. One contribution comes from the vacuum, and in the holographic context, we can guess that this would be the contribution from the BTZ black hole, the highly spinning rotating BTZ black hole. And then there are non-vacuum contributions, which are where both H and H bar is above the twist gap capital T. And again, the capital T is a positive number. And the modular invariance basically relates this to quantities. And here, because here by Z, I mean the partition function corresponding to the Virasoro primary. So there is an extra factor of square root of 4 pi square root over beta L and beta R in relating this to channels. So this will be our modular crossing equations, and the idea is to analyze this equation in this particular limit where beta L goes to infinity, beta R goes to 0, and the limit is taken in this synchronized fashion. So we want to show that what kind of terms dominates in either channel, and then we want to make some prediction from this equation. So let's begin with this channel, which is a dual channel. So we have two terms. One is the vacuum term and one is the other non-vacuum terms. And as you can guess, the idea is to show that in this limit, this rate term dominates over all these other terms. And here it's important to show that so there are infinite number of terms on this side, in the green side, and the combined effect of this infinite number of terms is still dominant compared to this vacuum term in this limit. So to show this, in fact, if you go through this analysis, then we can show that this combined effect of all these terms here, this green divided by this red term, which is basically the BTZ contribution, is given by this quantity here, which is beta L to the power 3/2, and then there is a exponential factor which comes with this prefactor here, 4 pi square over T over A beta R minus beta L. And now you can see that to show that this green term is subdominant and goes away in this particular limit, we need to make sure that this term goes to 0, and that precisely comes from this condition. And here also you can see if T is 0, then we are not in business, because if T is 0, then this e power A beta L grows, and in the beta L going to infinity limit, and then this is not suppressed anymore. So again, this shows that capital T has to be bigger than 0. And once we have this thing, we can do the following trick. We can take beta L and we can use this fact that beta R inverse is much larger than beta L. So I can replace beta L with beta R here, and I do not lose anything. And in the next step, I take this function here and I break it into two pieces. So you can see that here I have e power minus w square times the piece coming from the previous step. And here I have 1 minus w square. Now the idea is that if w is a fixed number, which we have chosen here, then this term goes to 0, as beta r goes to 0, because this is exponentially suppressed. And this term also goes to infinity, so this term also goes to 0. So by choosing this careful limit, we have shown that the green term is indeed suppressed compared to the red term. And here the most important thing is the presence of t and the presence of this simultaneous limit, which makes sure that the green term is suppressed. So once you show these things, you go to the direct channel, and in the direct channel you again have 3 terms, and then again you need to go through a bunch of inequalities, which basically shows that this term here, which is the low twist terms, are suppressed compared to this red term, which is the BTC black hole. And again, the high twist terms are also suppressed compared to these things. So whatever remains is basically here, and this has to reproduce the singularity coming from this Z vac or of the BTC black hole. Okay, so the key technical idea so I'm not going through the details of the proof, but the key technical idea in proving all this kind of identities is to choose some beta 0 which lies between beta L and beta R. Because we are taking a double Lightcone limit, the beta L goes to infinity and beta R goes to 0. So we can always choose a fixed beta 0 which lies in between. And then the idea is whatever quantity we would like to bound, we would like to write down some inequality of this form. So on the left hand side, we have some quantity to bound, which is less than equals to some known function, which depends on beta L and beta R, times some partition function evaluated at this beta 0 comma beta 0. And the idea is because beta 0 is fixed and we know that there is no divergence in the partition function at some finite temperature, so this is a finite number. And this function is known. For example, this function can be something like this. And then we can analyze this function, which is basically a bunch of exponentials with polynomial separations of beta L and beta R. And we can write down, we can show that all these green terms are suppressed and the red term is dominated. And red term dominates the dual channel. And from the direct channel, this singularity has to be reproduced by this piece here. So basically, we have shown that by doing this logic, we have shown that there has to be infinite number of states in this strip. And because, okay, before that, we also need to show that if you just pick a single state from this interval, it cannot reproduce the singularity on this side. So which basically means there has to be infinite number of states whose combined effect is to reproduce this vacuum term here. So this basically shows that given any epsilon greater than 0, there are infinite number of states in this interval, which amounts to saying that this A is an accumulation point. And now you can ask, once you show that this A is an accumulation point, which is C minus 1 over 24, you can ask how many states are there for each spin inside this interval at large speed. And another set of questions is, here we said that given any epsilon, there are infinite number of states, but at this point we do not know how epsilon behaves as a function of large spin, as a function of spin. So we can ask, how small can we make this window as a function of spin? So can we make epsilon as a function of j smaller and smaller? And supposedly, can we make epsilon of j go to 0 as j goes to infinity? And it turns out, in fact, we can. And even then, there are infinite number of states in this interval, and we can actually estimate how many of them are there. Is the goal clear? So.
Your T and A are
Say?
T and A are.
Yes, T is the twist gap, and A is C minus 1 over 24, sorry.
And T A is the bound.
Yes, T is less than equals A. Yeah, that's right. In fact, that's the consequence of this theorem, basically. This result. Okay. So now we can also try to do the same analysis in the large central charge regime. And in the as I was saying, in the if we look at a family of CFTs with central charge going to infinity, then the dominance of this vacuum term basically means dominance of near extremal rotating BTZ black hole. But then there are certain caveats when you want to do the large central charge image. I would like to remind you guys of this result by Hartman, Keller, and Stoica, where they prove a Cardi-like formula about large central charge CFTs, but then they also need some sparseness condition on the spectrum, which basically means that if a CFT has to be holographic, they need to satisfy some extra conditions. So here also we will see that if we need to prove if we want some dominance of this kind of terms in the large central charge limit, we need some extra sparseness condition, which is not exactly like the one proposed by Hartman, Keller, and Stoica, but slightly different one, which is basically a sparseness in the twist spectrum. So in particular, we have to impose these two conditions. So first of all, we have to impose that the twist gap is bigger than equals some order 1 number times central charge, except for finite number of states. So which basically means that there is a number alpha such that if C goes to infinity, there are always, as C goes to infinity, alpha times C also goes to infinity. But there exists some number alpha such that the number of states below alpha times C is finite. So that's the incarnation of the sparseness condition in this context. And intuitively speaking, it feels slightly stronger than the sparseness condition imposed by Hartman, Keller, and Stoica. But we need this condition to prove the dominance of the BTZ black hole. And not only that, we also need to impose this condition. This is some uniform bounded net condition, which basically says that if I look at beta L and beta R, which is greater than twice pi, the Hawking phase transition temperature, the most of the contribution comes from the vacuum. So basically Z over Z vac has to be bounded by some number, which only depends on beta L and beta R and does not depend on the central charge. So this, I do not have a very physical intuition about this condition, but it turns out the fact that this number is uniform in central charge is crucial to put bounds and make sure that we can prove that this term dominates. And this comes about because of the following reasons. Earlier I told you that the main technique we use is that we are bounding some quantity by some known function and the partition function evaluated at some fixed temperature. But now the problem is that if we do not impose this extra condition, then this can also blow up, even if it's a fixed temperature. This can blow up as the central charge goes to infinity. So to bypass this technical problem, we need to impose this condition. Anyway, so under these two conditions, we can show that this vacuum term dominates. So basically, which means the BTZ black hole dominates. So again, the beta R goes to 0, beta L goes to infinity, and earlier I explained so earlier I said that beta L and beta R has to be, this limit has to be taken in a certain synchronized way. So here we can take a weaker limit, which basically says that 4 pi square alpha over beta R minus beta L has to be bigger than equals some number times central charge as central charge goes to infinity. In this limit, it's possible to show that this dominates.
So I guess on the previous slide, that one that T less than alpha,
Yeah.
T greater than alpha,
Yeah.
with finite number. So if you just have like a KK reduction or something like that, does that pay that? You just have gravity history time or something about what KK modes.
Yes. Are you saying the KK reduction will introduce some states here? In that sense?
Well, I'm just saying about the infinite tower of KK modes.
Yeah, I guess if there are infinite towers of KK modes, then that can potentially spoil this result. And which might be related to the fact that, so I think there is some confusion in the literature because in earlier people have said that they can see Schwarzian sector in the 2D CFTs, but they are not entirely very much careful about all these limits and everything. So here this and then people said that, well, if I want, so in the literature, when people say the Schwarzian sector dominates, they do not really cleanly separate out the Schwarzian sector from this other stuff, these KK modes and everything. And they said, well, there is some contribution coming from the Schwarzian sectors, and there might be some comparable other contributions, but we are not talking about them. Here we want to, on the 2D CFT side, we want to separate out the Schwarzian sector concretely. So we need to impose this extra condition, because otherwise there is no separation and we cannot say this is the one that dominates. Yeah. So in some sense, in the CFT analysis, like if you do it carefully, there's nothing to hide. Like, so everything is crystal clear, and so you have to impose. And also there is another thing I will mention, that here also when people say Schwarzian sector dominates, it's important to mention which ensemble they are talking about. Because going from grand canonical to microcanonical, things might change, and that gives you another set of complication in the story. So yeah, so for example, like if we just want to say that the vacuum term dominates here, we only need to impose this condition, which is much weaker than this condition. So here, this is much stronger condition than the one appearing here. So depending on what kind of result you want and what kind of ensemble you want to state your result in, these conditions might change. Okay. So as I was saying, that if we just impose these two conditions, then this allows us to choose beta L to be order C and beta R to be C inverse. And then this is what this paper by Henry, Huopin, and Olmik basically claims, that they can see the Schwarzian sector. So when they say they can see the Schwarzian sector, basically they mean that in this grand canonical ensemble, if you take this limit, you can see the Schwarzian sector because you can choose beta L to be order C. But this story doesn't go through when you want to go from this grand canonical to a microcanonical ensemble, and there are other subtleties. Okay, so now we go to the microcanonical ensemble. So here in the previous slide, I only analyzed the dual side. In the direct channel, there are 3 terms, and ideally we should ask that what can we say about the dominance in the direct channel, because we want to show that these 2 terms drops out and most of the contribution comes from this narrow interval around C minus 1 over 12. And if we really want to do that, if you want to show that this 2 term drops out, then we have to take this more complicated limit. And in this more complicated limit, we are not allowed to choose beta L to be of the order C, because here beta L over A goes to infinity. So if you like, if this is too much technical details, the main lesson is that going from the grand canonical to the microcanonical, things change. So just saying something dominates in the grand canonical doesn't automatically guarantee the same thing dominates in the microcanonical ensemble, because there is an inverse Laplace transformation involved, and that will change, that might change things. Okay, so here's the main do's and don'ts in the large central charge regime. So if you just want to say the vacuum dominates in the grand canonical ensemble and you want to see the Schwarzian sector, you can choose your beta L to be order C. If you want to do it in the canonical ensemble, where you just flip flip the beta R to replace the beta R with this conjugate variable spin, then also it is fine. Beta L is order C. But if you want to go to the microcanonical ensemble, where basically you are looking at some small interval around in the age variable, then beta, you cannot choose beta L to be order C. To cleanly separate things, you have to make sure that beta L over C goes to infinity. So again, the point is that the grand canonical and the canonical behaves a bit differently than the microcanonical ensemble. Okay. And when so say we impose this extra condition that beta L over C goes to infinity. In these conditions, in this limit, we can show that most of the contribution comes from this interval. And again, you can ask the same question, that there are infinite number of states in this tree. So how many are there for each spin j, as j going faster than CQ? This basically comes from this limit here. And again, the other question is, how small can we make the window as a function of spin as we go higher and higher up? Okay. So now I will briefly sketch how we do this procedure, how we count operators. How can I transform this equation, some statement about the grand canonical ensemble to some statement about the microcanonical one. So we would like to estimate this quantity nj epsilon, which is basically the number of states in this interval, a minus epsilon and a plus epsilon with fixed spin j. And you can also consider a more general quantity where you have two-sided interval with epsilon 1 and epsilon 2. And again, you count the number of states with fixed spin in this interval. And the aim is to prove some asymptotic behavior of this quantity nj as j goes to infinity. And we can also try to make epsilons go to 0 as j goes to infinity. Okay. And so the results we can show is the following. So we can show that if epsilon goes like j to the power minus half log j, so as j goes to infinity, this goes to 0. The number of states in this interval go like exponential 4 pi square root aj times some polynomial separation in j. And then there is some f kappa j, some error term which we can bound by this logarithmic quantity. So here the main important point is that, so this is what you would expect if you just write down a naive Cardy formula and integrate the naive Cardy formula against this interval. But here the point is, here we actually show that even if you make the window small as j to the power minus half log j, we can trust Cardy formula and integrate, and we would get this result with some error term which we can control. So in this regime, the Cardy formula can be trusted for a window which goes to 0 in this rate. And this number kappa, you can see that kappa depends on this capital T, which is the twist gap. And again, if you set the twist gap to 0, this kappa goes to infinity, and then this becomes meaningless. So again, this formula shows that having a twist gap is important to prove this kind of results. Okay, we can also do the same thing for the large central charge. And here we have epsilon 1 and epsilon 2. And these are some details, but the main point is the epsilon 1, the scaling of epsilon 1 and epsilon 2 is different compared with respect to A. And again, there is a Cardy-like growth, and there is some error term which we can bound. And if you look carefully with epsilon 1 and epsilon 2 in this limit, you will see that both of them goes to 0 as spin goes to infinity. And again, the point is there are exponentially large number of states around this twist accumulation point as spin goes to infinity, even if I make the window smaller and smaller in this rate. And in the large central charge regime, as I was saying, that depending on so basically this is the claim from this paper by Onemic, Henry, and Walking, where they say that there is a Schwarzian sector where TH is order C inverse, which is same as saying in this language beta L is order C. But then this statement is only true in the in the grand canonical ensemble, if we want to go to the macrocanonical ensemble and claim the same thing, that the things are dominated by this middle regime, we should be looking at this regime rather than this regime. So this is the regime what we explain in our paper, where TH is very, very smaller than C inverse, and it is lower bounded by square root C over J. And also I should make one more comment here that, so normally when people talk about Schwarzian sector, people know that you cannot make this temperature very, very small and expect the thermodynamics to hold. And the general claim is that you cannot make these temperatures exponentially small in spin. And so once you hit the regime where temperature is exponentially small in spin, then the thermodynamics has to break down. But here we show that in some sense the thermodynamics breaks down much enough, like you do not need to go to exponentially small in spin. It basically breaks down whenever TH becomes of the order of square root C over J. And this effect comes from considering the non-vacuum terms in the dual channel. So most of the time when you do a gravity computation, you do not see effect of this non-vacuum terms in the dual channel. We only talk about BTZ black hole and some SL2Z image of the BTZ black hole. So if you just forget about this piece, then you would predict that this is exponential minus square root J on this side. But if you have the effect of this non-vacuum terms, you will see that you can only trust this kind of analysis up to square root C over J, not lower than that. So it might mean that for holographic CFTs, we might need to impose more conditions than what we assume here. Okay. How am I doing with time?
15 more minutes.
Okay. So now I will give you a very quick sketch of the proof, like how we do it. And so as I was saying, we want to estimate this quantity here. And one way to estimate this quantity is to insert this exponential factor here, e power minus h minus a beta L, because it's in some sense AJ is some smoothened out version of NJ, so it's easier to estimate AJ. And this AJ and NJ are related trivially because we can write down this inequality, because h minus a is between minus epsilon and plus epsilon, so this inequality is true. So if we can estimate this quantity AJ, we also have some estimate of NJ. So we bypass the problem of estimating NJ to AJ here. So now what is AJ? AJ is basically we are counting some states in this small box with fixed spin J, and we are counting how many states are there with some exponential damping with e power minus h minus a. Now, because speeds are discrete and there are only integer spins, I can elongate this box and I can make it like this. So the number of states here is same as the number of states in this large box, which basically means I can define another quantity where we not only smear over this direction, so we smear over both h and h bar. So here I was only smearing over h, and this size of the window on this side was very small, but now I am making it big. So I am defining this quantity script A, where I have smeared over h and smeared over h bar. And the claim is that AJ beta L epsilon, this quantity is same as this quantity as long as the smearing in the h bar direction, which is delta, is in this interval epsilon times 1 minus epsilon. So this inequality is just a fancy way of saying that, the quantitative way of saying that the number of states in this window is same as number of states in this window, as long as this red box does not touch these other blue lines. So now we want to so basically we want to estimate this quantity. So this is the quantity we want to estimate, and then this is the other quantity we defined. And as I have said that these two things are same when delta is in this interval. So I can estimate these quantities separately using the Tauberian formalism, and then I can take the limit. And here I have to make sure that the estimation I am doing is uniform in delta, so that I am allowed to take this limit and estimate this quantity. So all the estimation I will be doing in the Tauberian formalism of this quantity will be uniform in delta. So now a very quick recap of the Tauberian formalism, which basically tells us, given like how can we estimate the density of states by smearing it over some small interval. So the way to do it is to, like, I will not explain in very details, but just I will explain it in the context of the naive-Cardy formula. So in the naive-Cardy formula, the idea is to estimate the asymptotic density of states for a 2D CFT. So we take rho of delta, we do an inverse Laplace transformation of partition function, which is basically a Fourier transformation in this direction, if we are allowed to think about complex temperature. And the naive idea is in the high temperature limit, this integral is dominated by the t equals 0 point. And that basically gives you some smooth approximation of this rho of delta, because you can estimate this integrand by using modular invariance. But this intuition falls flat because of recurrence, because z of beta plus it, if you wait for large enough time, it will repeat itself. So t equals 0 is not really a dominant point. So, and this integral is not even well defined, because rho delta is a distribution. So at some point it is infinity, at some point it is 0. So the idea is to regulate this integral by some compactly supported function of t, and by cutting off this integral somewhere. So you cut off this integral by introducing some phi hat of t. But then the problem is that once you introduce this phi hat of t, the left-hand side also changes. So you also need to have some control over the left-hand side, because you, at the end of the day, you want to estimate the density of states. So to control the left-hand side means you want to impose some extra conditions on this phi hat of t beyond the fact that phi hat of t is compactly supported. And these kind of things are very common in number theory. So we just need to borrow that technology. So the idea is to look at the Fourier transform of phi hat of t, which basically gives you a function in a delta variable, phi delta. And you want to choose this functions phi hat of t in a way so that phi plus and phi minus basically approximates these characteristic functions from above and from below. So our original goal is to estimate the number of states inside this box. So basically, which means the rho delta convolved with these characteristics functions. But now instead of using the characteristics functions, I can convolve rho with this phi plus and phi minus, which is a approximation from above and below. And because rho is the density of states, is positive, so even when I convolve with these functions, this inequality is preserved. So basically, I take the density of states, I convolve with this function, and then I go to the Fourier variable, and then it basically becomes an inequality of this form. So where in between I have number of states, and as a lower bound and as an upper bound, I have some integral where I have partition function evaluated at complex temperature multiplied by some compactly supported function, where the support goes from minus lambda to plus lambda. Now all these integrals are well defined because they are finitely supported. And then the main aim is to use modular invariance and estimate this integral, and show that the upper bound and the lower bound has a similar Cardy-like growth. And then by sandwich theorem, it basically means the number of states has to grow like that. So this is what I said, that you basically write down this equation, then you go to the dual channel where you replace z of beta plus it with the S transform version. And then there are two pieces. One is the light piece, which is a vacuum contribution. This gives you the asymptotic growth, the usual Cardy formula. And then there is a heavy piece. And basically you have to show that the heavy piece is like all the non-vacuum states, they are suppressed compared to this light piece. And to make sure that they are suppressed basically forces you to choose lambda is less than equals twice pi. And if so, turns out that this lambda is basically related to the inverse spacing. So the fact lambda less than equals to twice pi basically gives you an upper bound on the spacing of Virasoro primaries as large delta. So when all the dust settles, you can prove some result like this, where rho zero delta is some known function, which is basically the Cardi formula. And you are counting the number of states from delta minus, like in this interval, as capital delta goes to infinity. And then you can show that this is upper bounded and lower bounded by these numbers. And now you can also see that if my twice delta, little delta, is bigger than 1, then the lower bound is positive. And that means there are exponentially large number of states as long as my interval has a size 1. So it basically means that in any 2D CFT, the spectrum of Virasoro primaries cannot be sparse than this. The gap between the consecutive Virasoro primaries has to be upper bounded by 1. It cannot be sparser than that. So we basically use this technology in our context. So earlier I told you about this density of states. So now this quantity is replaced by this quantity A, which is basically density of states with this factor, but now we have smearing over H bar and H instead of delta. So earlier we had the partition function evaluated as beta plus IT. Now this thing gives rise to this quantity where it's not the full partition function, rather it's only counts the contribution of the partition function from this from this narrow window around A. And the partition function is evaluated at beta L, beta R plus IT. And earlier we had modular invariance, so we had equations like this. And now on this, again, we have some modular invariance. So we write down some modular Gaussian equation. And to estimate the density of states, we just need to take this equation and integrate the FO with some compactly supported function, pi hat plus minus, and repeat the same procedure. So when the dust settles, basically we can estimate this side by just using the technique that we developed before. And for this part where we have low twist and high twist, the main idea is to get rid of the imaginary part because there is beta R plus IT here. And so basically you use bunch of triangle inequalities. And then we apply the techniques that we developed in this paper with Slava and Jaishin back in December. And then we extend the analysis so that this epsilon can be made smaller and smaller and go to 0. So by using all this machinery, we can prove our theorems. And here, just for sake of completeness, I will just flag the theorem. So it basically says that take any unitary modular invariant 2D CFT with central charge greater than 1 and unique normalizable vacuum and a twist gap which is greater than 0 in the spectrum of non-trivial Virasoro primaries. Then we can show that the number of states basically, which AJ basically counts the number of states, divided by the naive Cardi formula, which is this, is upper and lower bounded by these precise functions of epsilon and W. And these numbers basically comes from some particular choice of phi hat, which is again widely known in math literature, which is known as Boerling-Selberg functions. And one can prove a similar result for large central charge with non-symmetric window around 8 in the same kind of theorems. And once you have this theorem, you choose appropriate beta L to translate it to a statement about the number of states. Because as I said previously, that once you have an estimate about AJ, you have an estimate about the number of states. So I will end with some final remarks that it's possible to extend our results with larger chiral algebra. So when you have larger chiral algebra, that means basically we have more states with h, 0 and 0, h bar, and there will be infinite number of such states. So either one can impose a twist gap with respect to this larger chiral algebra and deal with the characters of larger chiral algebra and repeat this analysis to gain some result, to prove some result. Or one needs to estimate the contribution coming from this infinite set of states of the form h, 0 or 0, h1. And it might be possible to connect these results with the Virasoro mean field theory, which is again some field, which again comes from some naive analysis of 4-point correlators and inverse Laplace transformation. So it might be possible to connect the Virasoro mean field theory with our story. There might be some connection to chaos because normally people expect that this 2D CFTs with a twist gap in the Virasoro primaries has to be chaotic. And so it might be possible to, and this chaos is and generally chaos is always in the asymptotic spectrum. For example, you can think of distribution of zeros of Riemann zeta function, and this asymptotic zeros has some chaotic properties. So you can think of our results as a way towards ultimately proving chaos in this asymptotic spectrum. So you first need to show that the spectrum is very dense, which we show here in the twist spectrum is dense. And then you need to show that if you assume some extra conditions on this CFT, then maybe you'll be able to prove the chaotic nature inside this dense spectrum. But this is more around some speculative thoughts. And one can also ask whether there is dense spectra at fixed spin, large scaling dimension, because here we showed at small twist, large spin. People expect similar thing might also happen at fixed spin, large scaling dimension. At this point, we do not have any result in this direction, but it might be nice to have some. And finally, like as I said, that in the Schwarzian sector, there are some subtleties in which ensemble you pick and so on. It might mean that to actually show that there is a Schwarzian sector and to actually show what we expect from the gravity, we might need to impose more conditions on the CFT side, this might help us to list down all possible conditions for a CFT to be holographic and so on. And that's it. Thank you.
So you have, so in your result, you have a parameter W. Is there like a optimized W, but in the strongest result?
Yes, you can do that. So here you have this expression W, and I think as you take W to 1, this probably becomes stronger. I think so. Or maybe not, right? Sorry. Yes, as you make W to 1, this becomes smaller. So this becomes smaller and sorry, the other way around. So this goes to half. Yeah, your answer is yes. And probably either of this limit would be the one. It might not be the same in both for the upper limit and the lower limit. Also, another thing is because epsilon, like if you choose epsilon to be this log j over square root j, the epsilon goes to 0. And then this sine function goes to 1 because it's sine x over x. So like in some sense, if you do not choose to be epsilon to be a finite number, rather log j over square root j, you can get rid of this and just put a 1 here. Nothing goes wrong. So you can get rid of W also in that limit. And the same is true for on this side. And if you put epsilon to be order 1, then I think, yeah, either half or 1 should give you the maximum one. Need to be, yeah, you just need to take the function and extremize.
You mentioned this thing that the microcanonical and canonical ensembles are dominated by different temperatures.
Yeah.
What is supposed to be the physical meaning of that?
Yeah, well, I would tend to say that, so normally when we say that microcanonical, normally when we think about ensemble, we always assume the ensembles are equivalent. But here ensembles are not really equivalent. So I would think that in terms of physics, if I think in terms of black holes, then I would think the microcanonical ensemble is the more physical one. Because you have mass and spin rather than temperature. Those are the derived ones. But yeah, I don't have a very good answer for that. Because normally the only reason people say Cardy formula matches up with the black hole entropy, because Cardy formula gives you a count in the microcanonical ensemble. And for some reason we'll have to think about black holes in the microcanonical ensemble. Because otherwise we could have declared victory in the canonical ensemble also. Like just compute the BTC black hole, compute the partition function, and show that it matches with the Cardy formula in the beta going to 0 limit. Like just the modular transformation. You do not need to do the inverse Laplace. But the reason we love to do the inverse Laplace, because we want to state in the microcanonical ensemble, because it makes somewhat sense to talk about black holes with energy and speed. So in that sense, I would think the microcanonical ensemble is the better one. But to be honest, I am also not happy with this answer. So.
Any more questions? Okay, then let's thank Sridip again.